Okay, so 8.4 is actually the first section in Chapter 8 that we start with. Chapter 8 is all about linear functions, graphs, models. Anytime you see the word models, think word problems. We're going to try and apply this so that you can see that math is applicable to the real world. And so Chapter 8 is what I would call your algebra chapter. It's actually, I think, our shortest chapter as well. So Chapter 2 was all about sets and how do we utilize sets in the real world, what are sets, and how do these work. Chapter 8 is more your traditional algebra, solving equations, graphing lines, finding slope, that kind of stuff. So hopefully none of this is brand new material. It just might be refreshed, or it might be looking at it from a different perspective. And so before we can actually dive into problems, though, today, we do have to have a set of definitions so that whenever I speak of a relation or I talk about the range of a function, you know what I'm talking about. So a relation is simply a set of ordered pairs. It's a relationship between two different values. And in this case, if we think about it in terms of our ordered pairs, it's a relationship between our x values and our y values. Our x values are the independent variable. That means they do not depend on the y at all. We get to pick them most of the time. We get to say, okay, I want my x values to fall from 0 to 10. What happens to my function in that specific area? Once we have picked our x's, our y's will then be brought out of our function or out of our relationship, and those are dependent. They are dependent upon whatever our x is. We will see this in just a few minutes in our very first examples as we test out various solutions. And what we will do is we will plug in different x values and we will chug out our y's. And our y values depend on what we're putting in. What value of x are we actually putting into the problem? That is why these are dependent variables. So a relation is just showing a relationship between two different items. But in this relation, we have what's known as the domain. That is the set of all values taken on by the independent variable. AKA, these are all of our first components. Your domain deals with your x values. We will look at different functions and we will say, okay, where is the domain? Where does this function exist? Does it only exist from 1 to 2? Or does it exist for all x values? Is it limited to a specific area? So domain is your x values. Your range is the set of all resulting dependent values, aka your second components, aka your y values. So the way that I can remember that domain goes with my x's and range goes with my y's is they're alphabetical, just like x and y are alphabetical. Domain D comes first in the alphabet, so does x. So they are connected. The range deals with my y values. Are there questions on what a domain and what range are? Right now they're just kind of definitions free floating out there, and we're actually going to see what that means though as we move forward. Okay, I'll slide up. I'll try and keep range still in there. Actually, I might be able to keep both in there for a little bit. Function. A function is actually a specific type of relation. Not all relations are functions, but all functions are relations. A function is a set of distinct ordered pairs in which no first component, or x, is repeated. That means every x produces a unique y. And if you think about a function like a machine, what that means is that every time I put the number 2 into a given function, I'm going to get the same y out. There's never going to be a chance that I put 2 into a function machine and I get out the value 1 and then sometimes I get out the value 0. That's not a function then. Every time I put in the number 2, I have to get out the same value, the same output. From a graphical standpoint, a function passes what's known as the vertical line test. Meaning if you can picture the graph, or if they give you the graph of a specific relation and they want to know if it's a function or not, draw a straight line vertically through it. If it hits on only one spot, yeah, it's a function. If it hits in more than one spot, it's not a function. A relatively easy example to see this, even outside of having to know how to graph these things, is if we look at the graph of a circle versus the graph of, let's say, a parabola. Both of these are different types of relations. And if we stick these on a Cartesian coordinate system, that's fine, just so that we have some reference to go off of. For a circle at point 1, notice what happens. If I move up on my circle at point 1, I hit my circle right here. But if I move down on my circle at point 1, I hit my circle right there. That means if I draw a vertical line right there, I would hit my circle in 2 distinct points. If I put 1 in, I can get either this top value or this bottom value. This is not a function at all, because it would not pass my vertical line test. This is a relation, but it's not a function. You can't read that because it's not on your screen. Bloop. There you go. A parabola, though, these are our quadratics. These do pass vertical line test. These are functions. For each and every x value, there's only one y value that's going to happen. Over here, my x values are going to hit in more than one spot. They produce more than one y value, which is why those are not functions. So all relations are functions, but not all functions are relations. A function is a specific style of relation where each x will give you just one y value. Okay, let's look at function notation. Function notation is where we take an equation, like y equals 2x plus 3. We can change that into function notation simply by substituting f of x in place of the y. That's all you're doing. So instead of saying y equals something, we're going to say f of x equals something. That's how we say it is f of x, or we say the function at x. It's just a different way of notating something. It doesn't really change anything, but it does make some of our problems a little bit easier because we will be evaluating our functions at different values. And then they become what I like to call plug and chug problems. We plug in a value, we chug out the solution. So just know that if you have y equals something or f of x equals something, you're really doing the same thing. All of your original math and algebra stuff still holds. Order of operations still holds. How we solve equations still holds. Nothing is changing. Just how we are designating it. So let's do an example. We are going to evaluate the given function f of x equals a negative 2x plus 3. This is the function that they give us. And we are going to evaluate this function at a couple different values. We have f of 0, f of 1, f of 3, and then we have f of x equals 7. One of the reasons why function notation is really nice is that we see that this is the function at x. And then it gives us a generalized equation of what's happening in this function with an x in there because we don't know what x is. We get to assign the x value because it's our dependent variable. In this first example, it says f of 0. Notice that 0 is inside our function in place of where the x is in our function notation. So that's what we're going to do with the 0 in the equation itself. We're going to substitute our x for the 0. So when I do f of 0, what I'm saying is that I'm going to take negative 2, and then instead of timesing it by x, I'm timesing it by 0. Negative 2 times 0 is 0, so f of 0 is just positive 3. And what I've actually done here is I have an ordered pair, because this is my x, and this is my y whenever I put that x into my function. So I can write this as 0, 3. You will have to read the instructions next to your answer box on Pearson to see if they want an ordered pair or if they just want to know what f of 0 is. If they just want to know what f of 0 is, there will be a little box and you just type in the 3. If they want an ordered pair, then in blue next to the answer box it will say state as an ordered pair. And then you'll give the ordered pair. If you do not include parentheses, it's not an ordered pair. It's just a listing of numbers and Pearson will count you wrong. So for f of 1, we do the exact same thing. Except this time, instead of plugging 0 into our function, we are plugging 1 into our function, and we're going to figure out what happens. So f of 1 will be negative 2 times 1 plus 3. Well, negative 2 times 1 is negative 2. Negative 2 plus 3 is a positive 1. So my ordered pair in this case would be 1, 1. Nothing changes at all when we do f of 3, except we're plugging in 3. Negative 2 times 3 plus 3. Negative 2 times 3 is a negative 6. Negative 6 plus 3 would give me a negative 3. So my ordered pair in this case would be 3, negative 3. Are there questions on these first three, on how we're plugging these in? In this example, they did give us all nice numbers to plug in. You could have fractions to plug in. You could have things that say x minus 1, and you have to plug those in. And so it might not always just be a number, and that's okay. You do it the exact same way. You plug it in, and you simplify it down. Yep, I'll show you one. I don't know if you encounter one or not, but I will show it to you. Let's pretend it said find f of x minus 1. We don't do this any differently than we do f of 0. Anywhere in our function that we have an x, we're now going to put whatever is inside of here. So now it says x minus 1. So that's what we're going to put in place of x. So instead of negative 2 times x, I will now have negative 2 times x minus 1. Whatever is in here goes wherever my x was. And now I would simplify. I simplify by distributing the negative 2. Negative 2 times x is a negative 2x. Negative 2 times a negative 1 would give me a positive 2. And then I still have this plus 3 out here. Whenever you have an x still within your function, you will not get a nice ordered pair. You would just get another expression. Because this one still had an x at play. So this one still has a variable that we don't know what that is. Again, I don't know if you guys actually encounter any of those. I can flip through your homework at the end of this class and I can look. I don't think you do, because I would have worked an example out like that if you did. But it's always good to know. Stuff like that does come up. Whatever is inside of your function, you plug in place of your variable, you simplify. Now, what about D, though? D looks a little bit different. D doesn't say f of 7. It says f of x equals 7. So what do you think we're going to do this time? What do you mean?
So, for example, it would be -2 because our equation is -2x plus 3. So you plug in -2, which equals 4 plus 3, which equals 7.
Okay. What if this was a harder equation, though? What if this said -253x plus 7/4 minus the square root of 36? Like, then it's a little bit harder. With a relatively simple one, your process isn't necessarily incorrect. It's just limited to how complex the equation is. So notice that this says f of x equals 7. So where up here there is an f of x, we're going to put a 7. This whole thing says f of x, and over here it says it's 7. So instead of writing f of x, I'm now going to write 7 equals -2x plus 3. And then we're going to work through the algebra to actually figure out the x value that you just told me. This method will allow us to solve more complicated equations, but still come up with a solution like you just stated. So this one is different only in that here we were replacing our x values with 3 and solving and figuring out our y. Here, in essence, they gave us our y value, and we got to figure out what x value works for it. So how would I solve this equation? What is the first step? Yeah, we're going to subtract 3. We got to get our variable by itself, and so we start by moving the numbers that are most removed from our variable. That -2x is attached because it's multiplying against the x, but this plus 3 is kind of added on at the end, so we can subtract. We think about doing the opposite. 7 minus 3 is 4, and we have -2x left over on the right-hand side. Now what do? Divide by what? -2. We got to divide by -2 to get x completely by itself. Again, thinking of doing the opposite. This -2 is multiplying against the x. The opposite of multiplication is division. 4 divided by -2 would give me -2 as my x value. And you can always test this, plug it back in, and like you already stated, -2 times -2 is a +4, plus 3 would give me a +7. So this is the correct solution. And the ordered pair then for this one would be -2, (7).
I have a question.
Yes?
Why is 7 in the y place?
Because that's what they told us in this problem.
So f of x or f times x is equivalent to y?
It's not f times x. This is the function notation. And so this does mean f of x, which is the same thing as our y value.
Okay. So it'll always be y?
Mm-hmm. Always. Other questions? These are good questions. No? Okay. Let me flip over and we'll talk about linear functions. These are ones you've actually talked about probably a lot in your algebra classes over the years. Whether or not you call them functions or just linear equations, same thing. A linear function is a function that can be defined by a rule written in the form of f of x equals ax plus b, for a and b are elements of the real numbers. This little e, remember, means elements, and this funky r means real numbers. We're not going to deal with imaginary numbers, so a and b have to be real numbers. We have the breakdown of all of our numbers in Chapter 2. This f of x equals ax plus b is the same thing as y equals mx plus b. They just use a instead of m. The b, they use the same variable. But this y equals mx plus b is our slope-intercept form. This is the number one form we ever deal with lines. If you are asked for the equation of a line, this is always what they want. Why? Because it gives you enough information to graph. It gives you your slope, and it gives you your y-intercept. Slope is the difference of your y's over the difference of your x's. So what that means is you're going to deal with your vertical change over your horizontal change. How much does your line move vertically versus how much does your line move horizontally when we compare these two given points? The y-intercept, that 0b, tells us where our graph crosses the y-axis. When we think of our Cartesian coordinate system, we have a y-axis which runs vertically, and we have a x-axis that runs horizontally. So that y-intercept shows us where we cross the y-axis. And with just those two pieces of information, we can graph any line that they give us. Because what we do is we graph our y-intercept. That's a point. We graph it. And then we can use our slope to graph a second point. In order to graph a line, you need 2 points. And if that doesn't totally make sense yet, we're going to do some, and hopefully that will help clarify how you use the slope in order to actually graph a line. Chapter 4 in Math 20 is where we covered this material, if you took Math 20. If you did not take Math 20, that's also okay. I like to reference what other sections we cover in other chapters, because if you want to, you can go on my YouTube site, you can click on the beginning algebra playlist, and you can go back and reference those videos if you want some refresher on how do we find slope, or how do we graph whenever we have just a slope and a point and things like that. There's lots of good information there. All right, we're going to graph these lines that they're going to give us. We're going to graph the lines, then we're going to give the domains and the ranges of these lines. And the nice thing about them is they give it to us in a nice format. So here's our first line. We have f of x equals negative 2x plus 3. That's the one we've been playing with. That's the one we plugged all those values into. Now we're actually going to graph it, and we're going to see what happens. Remember that this function notation is the same thing as y. So this f of x is the same thing as y, and then we can write the negative 2x plus 3. And if this makes you more comfortable because you're used to seeing lines represented as y equals mx plus b, that's totally okay. The 2 is our m, and the 3 is our b. Well, m is slope. So the slope of this line is negative 2. And our b in this case is a positive 3. So my y-intercept as an ordered pair will look like 0, 3. And with this information, I can graph this line. All right, so here's my graph paper. You don't have to have graph paper necessarily. You can make your own Cartesian coordinate system with vertical, horizontal lines, and then put some little tick marks in. Although I will say these sticky notes that come as graph paper are very nice for note-taking. Amazon. So the first thing I'm going to do is I'm going to plot the y-intercept, which is 0, positive 3. So I don't move left or right, and I just move up 1, 2, 3, and I plot my point right here. That is the point 0, 3. And then I use my slope to plot another point. Now, according to our slope formula, which is still right here, we have our vertical change over our horizontal change. Well, when we have a whole number, there's no bottom number to be shown. So I'm going to always change my whole numbers into fractions by sticking them over 1. When you divide by 1, it doesn't change anything. It just helps represent what's happening horizontally. And that's what we need to know in order for us to graph with it. So if I have vertical change over horizontal change, the vertical change is my y change. So if I think about my y change being negative 2, do you think I'm going to go up or I'm going to go down? Down. Negative y's are down here. So the negative direction vertically is down. So this would mean I would go down. Now, my 1 on bottom is positive. And if that correlates to my horizontal movement. So horizontally, is positive headed to the right or is positive headed to the left? Right. It's headed to the right. These are my positive x values over here, so you head to the right. So in order to use my slope now to find another point, I'm going to go down 2 to the right 1. And I'm going to plot a point. I went down 2 to the right 1 from my y-intercept. I connect my 2 points. And I make sure that, at least on paper and pencil when I'm doing this, that I make sure there's arrows on my lines. When it comes to the midterm and the final exam, which are paper pencil tests, you have to make sure you have arrows on your lines to indicate that that's going on for forever in these directions. I keep going up and over this way, and I keep going down and over this way forever and ever and ever. That's what those lines are telling me. Are there questions on how I use the y-intercept and the slope to graph this? Okay, we're not done with that problem because it said give the domain and the range. The domain is your x values. So when I think about this line, and I think about it going on forever, ever, ever this way, and forever, ever, ever, ever this way, maybe it's easier to ask, are there any x's that I'm never going to actually use? Like here, this x value correlates to the line up here. This x value over here correlates to the line down here. So can I find an x value where I can't either move up or down and hit my line? No. So the domain is negative infinity to positive infinity. We write these in interval notation. We did a lot with interval notation, I believe, in chapter 10 of Math 20. That means it goes on for forever. Now let's look at our range. The range is our y values. So instead of thinking about, can I move up and down for my x's, I'm going to think, can I move right and left for my y's and hit my line? Is there ever a y value where I cannot hit my line? No. And here's a helpful hint. If you have a linear function, this is always your domain and range. Always. Because it's a line that keeps going, well, I say always. This is your domain and range if you have a non-vertical or non-horizontal line. Let me state it that way. If you have a vertical or horizontal line, then it's slightly different. Every other line will have a domain and range like this. And I actually do a horizontal line on the very next example so that you can see what changes. Questions? All right, let's do another one. We're going to do B, where we have f of x equals 3. Notice this one doesn't have an x term. If you want it to, you can rewrite it. So you have f of x equals 0x plus 3. Because when you take 0 times x, it's going to go to 0, which means it's going to go away. So if you really want it to look like y equals mx plus b, you can absolutely do this. And if you do that, hopefully it makes it really obvious what your slope is. Because the slope is whatever number is in front of x. So in this case, the slope is 0. And your y-intercept is going to be 0, 3. Back in Math 20, we talk about there's a special kind of line that has 0 as its slope. Does anybody remember what kind of line that is? The other one. Horizontal. Vertical lines, like our y-axis, they have lots and lots and lots of vertical change, so that would be your top number. No horizontal change, which is the bottom number, and when you divide by 0, it's undefined. So this is the opposite. To have 0 slope, you have lots and lots of horizontal change, but no vertical change. And so the slope would be 0 over any number. Let me switch to purple. My y-intercept is 0, 3 again, so I go up 3 and I plot this. Now, if I recognize that this is a horizontal line, I just drop another point anywhere on there and I make my line. If you don't recognize that slope of 0 means you have a horizontal line and you're trying to use your slope then to find another point, well, it's 0 over any number. So stick it over 1, just like we did our last whole number. This means we have 0 vertical movement and we move to the right 1 unit. So we can move to the right and we plot it. We still have a horizontal line. Horizontal lines will always look like y equals a number and there's no x value. Vertical lines always look like x equals a number. And this is one of those 2 examples where it does affect our domain and our range, at least one of them. So remembering that domain deals with our x values, is there any x value that I'm going to hit that's not going to hit that line? Like that I can't, at x is -3, I can go up and I can hit it. At x is +5, I can go up and hit it. Is there any x value that I'm not going to have that happen? No. It goes on forever to the left and forever to the right, so I can always go up or down and I can hit it. The domain for these will always be -infinity to infinity. Just like on the last one. My range, though, is a little bit different. My range is the y values. What y value is the only value I hit in this entire line? 3. I'm never going to hit 4. I'm never going to hit 0. I don't have any other number that I will ever hit, ever. And so the way that I represent that is I use a squared off bracket and I type in 3. Because 3 is the only one. Or sometimes you'll see it with curly brackets as the set. Either one. But there's only one value, and it's 3. So if you have a vertical line, these are going to switch. If you have a vertical line, let me just draw one in over here. This vertical line is at x equals 1, 2, 3. X equals -3. This is just like a bonus problem over here. Over here, for our vertical line, our domain is the thing that never changes because that's our x value. And we only ever have one x value, no matter what our y is, and it's -3. You can't see that. There. Our range, though, would work for everything. So they flip-flop. These are the 2 different examples that can happen. If you have any other line, as long as it's not vertical or horizontal, your domain will be -infinity to infinity and your range will be -infinity to infinity. If you have a horizontal line, you will have domain of everything and your range is whatever the range value is, whatever that y equals. If you have a vertical line, your domain is whatever x equals and your range is everything. Questions? Okay. Let's do our 2 word problems. So this is where you want to have that handout. If you didn't pick one up, you can pop up and go get one. We're going to see some real world problems for linear functions. Oh, I had that. That's fine. And I made the handout simply so you wouldn't have to write all this stuff down, because that's gross. It says Peripheral Visions Incorporated produces studio quality DVDs of live concerts. The company places an ad online. The cost of the ad is $100, and each DVD costs $20 to produce. And the company charges $24 per DVD. So express the cost as a function of F, the number of DVDs produced and sold. So we want to know how much does it actually cost, the company to produce a given DVD. Well, we know that the company cost for a single DVD is $20. But we also know that in order for them to market their DVD, they pay a $100 ad fee. So they're going to pay $20 per DVD and then $100 as an ad fee. So if we are doing a cost function to figure out the total cost for a DVD, what we're going to do is we're going to have the cost in terms of X, because it says express the cost as a function of X. So we have the cost in terms of X equals, well, it costs $20 per DVD, but we don't know how many DVDs they sell. That's what the X tells us. The X stands in for the number of DVDs. And we can't just leave it like that. It's not that simple, because the company also incurs a cost of $100 in order to run an ad. So we're going to put plus 100. So if the company only sells one DVD, it costs them $120 to produce that DVD. If they sell two DVDs, it's $140, and we can keep finding how much the company is going to incur in costs as they are making their DVDs. For B, it says express the revenue as a function of F, and that's the number of DVDs sold. Revenue is how much they're going to make. It doesn't mean profit. That's different. Revenue is how much money they're bringing in. So the revenue in terms of X is what it's asking for in B. Well, how much do they charge for a DVD? $24. And there's nothing else for that one. Because we don't have to pay them anything extra just because they ran an ad or anything like that. That's part of their costs. And so when you run a company, you have to look at cost versus expenses and all of that, and how much money you're going to bring in versus your revenue. This is a cost-revenue problem. And we have to find out in Part C, when will the company break even? That is, for what value of X does the revenue equal the cost? So they kind of help you there. When does the revenue equal the cost? So we're going to stick our revenue function and set it equal to our cost function. Because that's when the company actually breaks even. That's when the cost of making the DVDs will equal the amount of money they've brought in from selling the DVDs. So I'm going to have 24x, because that's what my revenue function is, equal to 20x plus 100, which is my cost function. And I'm going to solve to figure out how many DVDs they're going to need to sell in order to break even. So what do? I got x's on both sides. I need to figure out what my x value is. Subtract that 20x over. That's exactly right. Let's get all of our x's together. That'll give me 4x equals 100. Divide by 4, and I find x equals 25. So what this tells me is that they break even when 25 DVDs are sold. So not too bad. I mean, when you think about hopefully selling thousands upon thousands or even millions of CDs, you start actually making money on the 26th DVD. So that's not horrible, as long as people are actually still buying DVDs. So for part D, it says graph the cost revenue functions on the same coordinate system and interpret the graph. So I have a really nice one in my handout, and I'm going to use it to show you this, because on Pearson, they're not going to have you actually graph them. They're going to have you match a graph or read a graph. So I want you to see how these graphs work, because that's a lot nicer graph than I can throw up here in the next minute or two. This graph looks complicated. It's not. What we do is we take our cost function and we graph it. This is written in y equals mx plus b. The slope is 20 and our y-intercept is 100. So that's this line right here. I have a y-intercept at 100, and then I use my slope of 20 to move up and over and draw this line. This top line down here, which becomes the bottom line up here. That's my cost function. I did the same thing with my revenue. I have a slope of 24, and notice there's no plus number out here. So you can put plus 0, meaning your y-intercept is 0, 0. So I start at 0, 0, and I go up and over by 24 to give me this bottom function. And so the way that you can use this graph to help you find out information is that this top one is your cost. So notice here we just found that at 25 DVDs, that's where these two graphs, these two lines intersect. And that's because that's the break-even point. After this, notice that our top line becomes our bottom line. That's our cost. And our revenue becomes our top line. So all of this then becomes our profit. Until the break-even point, we are losing money as a company. We are not making anything, because every single DVD we sell, we're actually losing money on. But after 25 is when we start seeing profits. And our profit margin depends on how much we're selling versus the cost. A lot of times, once you hit certain numbers, like the cost goes down quite a bit, and it's not totally linear like this in the real world. But if the cost stays the same, no matter how many you produce, then you can use a linear function to represent this information. So math and algebra is legitimately good and helpful for running businesses. Because if you don't know where your break-even is, and you're only going to sell 20 DVDs of a given movie or a given concert, it's not going to go well. Your company's going to tank pretty quick. Because you've got to hit the profit margin. You've got to get up there. Are there questions on this one? Are there questions on how I did my graph at all? It looks scary, but it's not. It just has hundreds on the side and fives along the bottom instead of 1 by 1s. You graph the lines exactly like we do all of our other lines, though, because we have a slope and we have our y-intercept. We have a slope and we have our y-intercept. It doesn't really matter how big those numbers are. We still graph them the same way. Yes?
Did you just graph up to 1,000 just to show?
Yes.
Okay.
Yeah. Theoretically, it keeps going forever.
Okay. So
Yeah.
that's what I was confused with.
Yeah. No, that was just, I had a chunk of graph paper and I went up to 1,000. Theoretically, you could keep going for forever and ever. Yeah. Good question. All right, let's do our other problem, which is on the back of your handout. Oh, so sorry. Went in way too far. All right, this time we're going to look at tuition costs. That's a little bit applicable to you guys. It says the average annual tuition and fees for in-state students at a public 2-year college are listed in the table 2, which is this one shown. Let's graph the data in order to see what happens. It says let x equal 0 correspond to the year of 2013. Year 1 is 2014, and so on and so forth. What type of equation might muddle the data? So I will do a live graph for this one because there's only 5 pieces of data that we have to do. Well, that didn't peel apart very good. Again, on Pearson, you probably will not be expected to graph these. You will do multiple choice to figure them out. But this one's not a horrible one to do a graph on. Whenever you're designing your graph or laying it out, what you're looking for is what am I going to put where? Do I put my year over here and then the cost over here? Do I put the cost over here and the year down here? I'm going to put the year down here because we're going to start with year 0 and then move to year 1, 2, 3. And just to give us a little bit of spacing, I'm going to do every other line. So here's year 1, year 2, year 3. That went too far. Year 4, year 5. We only go up to year 4, to be honest, because we start with year 0. X is 0, 1, 2, 3, and 4. And then on the side will be our cost. Now our cost goes from $3,200 to $3,570. So I'm going to do thousands, I guess. That's why Pearson does multiple choice for a lot of these, because depending on what scale you're using will determine what your graph looks like. But I think going by thousands will work. So I have 1,000, 2,000, 3,000, 4,000, and $5,000. And I skipped one on mine just so that I have kind of halfway points, which will help me plot my points. So at year 0 in 2013, the cost of tuition was $3,264. So that's like halfway between halfway. In year 1, I was $3,345. So maybe a little bit higher than that last one. At year 2, I was $3,435. Year 3, I was just over halfway to 4,000. And I was a little bit higher than that in year 4. What does it kind of look like? Does it look like a parabola, like with a big U? Does it look like a exponential with a big swoosh up? Or what's this section called? So that you kind of get a hint of what it should look like. Yeah, we are in linear functions. It kind of looks like a line. It's not perfect, right? Each year, the cost is not going up exactly the same, but it's pretty linear. So we could represent this information as a linear equation to give a rough estimate of what the cost of going to college here is going to be, let's say in year 10 or year 20, because it is going up almost linearly. So that's the point of graphing it, is so that we can see whether or not it is following a linear pattern, and it kind of is. It's pretty dang close. So part B says find a linear function that models the data using the information for years 2013, so that's this one, year 0, and 2017, which is year 4. So they specifically tell us what 2 years. And it is important that they tell us what 2 years. Since it's not exactly linear, they have to kind of give us that information, because without it, our slope's going to be wrong. Because that's what we're going to have to find first. In order to represent this information as a linear equation, we have to find slope. And these years that they just gave us are our ordered pairs. Because this is our x value. It even says x equals 0, which makes this our y values. And to find slope, slope is y2 minus y1 over x2 minus x1. We need 2 ordered pairs for that. And they just gave us 2 ordered pairs. We have the ordered pairs 0, 3264, and 4, 3570. It does not matter which of these ordered pairs is your 0.1 and which one is your 0.2. If you wrote this one first, that can be your 0.1. It will not change anything. But especially as you're getting reacquainted with finding slopes, I usually label them. Because if I label them, then it's a plug and chug. I'm just substituting the values into the equation for my slope in order to figure out what my slope is. Because slope is going to be y2, so my y2 was the 3570, minus y1, which is 3264, all over x2, which is 4, minus x1, which is 0. That'll give me 306 on top, all over 4. And I'm going to round to 1 decimal place. On Pearson, it would be very specific and tell you how much to round if you have to give a decimal. So the slope is the 76.5. Just as a side note, this is the amount tuition is going up each year between those 2 years that we are testing. So if it was a perfectly linear line that we had when we plotted those points, it'd be 76.5 in between each of those dots vertically. So we're using this information as a really rough, really close estimate so that we can come up with an equation that will help us predict the cost of tuition. So now what we're going to do is we need to write this as a function. Well, my function notation, if you remember, is f of x equals, and we can write it as mx plus b. And we actually know all of this information now. We just found our m, and we actually started with one of our points being our b slope, like our 0b. So we already have that value as well. So to write this as a function, I'd write f of x equals the 76.5 times x, because that'll be times how many years we're looking at, plus my starting tuition cost, which was $32.64. If I'm dealing with the very first year of year 0, 2013, there's no price increase. So this would be 0 here, which means it's $32.64. If I'm looking at year 1, if it moves linearly, then we would be adding this 76.5 to the starting one, and so on and so forth. Are we getting what we're laying down here? Okay, it says part C, use this equation that we just came up with to approximate the cost of tuition fees at this university in the year 2018. So if we go up here to our table, 2018 would be the very next year. So 2018 is when x equals 5. And if x equals 5 and we have a function in terms of x, we can plug and chug like we did in our earlier problems, where we're finding f of 5. Well, when x is 5, instead of taking 76.5 times x, I'm taking 76.5 times 5 and adding to that my 32.64. 76.5 times 5 is 382.5. So 3646.50 approximately in the year 2018. Now, is that perfect? No, it's not perfect because our original data was not perfectly linear. But we can make some really close assumptions to at least make a trajectory and to make some educated guesses that kind of helps the college then make some important decisions on how to retain students, or does this line up with, cost increase at a worldly level? Does this actually mirror that? Because if the university is raising its prices exponentially faster than people are making money, then people aren't going to come to school. And so this is real information that universities do look at to try and figure out, how do we make our university actually cost efficient? One, so that students will come, and then two, so that we can actually run a university off of that information. So all of it's very applicable.